No.
But like,
It's pedagogical. It's clearly pedagogical because what happens is when you guys, I want you guys to do the problems and I want you guys to actually get the answers yourselves. What happens, and I know there's plenty of places where you guys can go and you can find problems with answers. When I post those handouts, the reason I don't post the answers isn't so you guys don't get feedback. It's so that if you want feedback, you got to go and talk to somebody. Because more than not, what happens is you guys go, you look at the answers, you spend a minute, and you go and you look at the answer, and you say, oh yeah, I could have figured that out. And I don't want that. There's plenty of answers out there. There's plenty of questions out there that you guys can look at. There's plenty of questions out there that you guys can find that have answers. My worksheets are meant in part so that you, if you struggle with those questions, you go and seek help. Because the feedback is equally as important. You might draw an answer, and you might think that that answer is right? But that translation can oftentimes be where everybody messes up. I think it's a fundamental issue, for example, with mechanisms. Come to my office hours. Absolutely, come to my office hours. Go to your recitation instructor. That's the point, right? Like you cannot, like everybody thinks that if they have the answers, then they can actually figure out what's going on. What I've seen time and time again is that students, I've had so many students come into my office, and they say, I knew that I knew this, and then I went to the exam and I didn't get it right. And it's like, well, it's because you didn't really know it. It's because you happen to be able to get that question, and a lot of times even the thought process, sometimes you got a 50-50 shot of getting the answer right, and you happen to get it, and then you move on. So I think it's really important that, that's why it's so important that you work in groups, right? Because you can't, and I understand, you need that feedback. You need to know if you're right or wrong. Absolutely, that's human nature. But there are plenty of questions where you can have the answers, and I view those handouts as really being, I don't want to post the answers, because I don't want you guys to have that ability to simply look at the answer, right? I really want you guys to work on it, and then if you struggle with it, come to my office hours. Go to your other recitation instructor's office hours. So it's pedagogical. It's clearly pedagogical, so I'm not like, no, I'm not doing it. But that's the reason, and you're, hopefully it wasn't offending, because you're one of probably 20 students that have already asked me that. So, yeah, but now I've recorded it, so now everybody can watch it and see. That's the reason. You need feedback, but if you look at the answer, there's a lot of interpretation issues, and if you look at the answer and you interpret that answer to mean something that it's not, and that's one of the big issues with mechanisms, is that you guys don't get feedback on mechanisms, and oftentimes you will see it drawn, and you will associate that mechanism with, oh, it's a bond-forming event, or, oh, it's those two atoms coming together, or something like that. And it's like, yeah, I can see how that interprets it, but it's the flow of electrons, right? And so when you associate an answer, right, because it's a language, if you begin to associate that language or that answer meaning to something else, that's the issue. And that's part of the reason why I don't post the answers on those. And they're, in a way, meant to be directly related to your recitation classes. So the hope is that you do them, and then the recitations is a great time to actually ask the specific questions that you get wrong, if that makes sense. And what I find is that when the students start getting the hang of all of it, you kind of know. When you get to the final answer, you're like, I know, this is right. I don't need an answer key. I know that I'm right. And even at that point, you can run it by your recitation instructor or something. So anyway, we're way ahead at this point. But hopefully, if you actually watch the lectures, you sort of realize that we haven't actually covered that much. Like, if you guys are feeling overwhelmed, it's probably because you're not as comfortable with mechanisms, and you're not as comfortable associating reactions with one another. I think that certainly we have a lot of reactions. Certainly organic chemistry is additive. But one of the things, right, about any class is that when you, in organic chemistry, anytime you are learning material, right, and you have to continue to remember this other material, once they all become new, right, and once everything is new, then you become overwhelmed. And, we're moving, and we're moving pretty fast. You've got to keep up. And I think that the quizzes are meant to have you keep up. And if you need an extra week, more than, say, for example, the people that took the quiz today, well, then why should you get an extra week over those people? So, yeah, you're going to be responsible for the material that's this week. They could get questions. That's the whole point of the quiz. Stay on top of material. You cannot plan your studying around a quiz in organic chemistry. You cannot plan your studying around an exam for organic chemistry. If you are not studying every day after class, right, keeping on top of the material at all points, then this course is going to be hell. If you maintain material, if you stay on top of everything, you put the time in week out, right off the bat, then what's going to happen, right? The course becomes a lot easier, right? Because everything builds upon everything else. And too often, we hold off, we try to do other things. So I know we're way ahead at this point, and so that's actually, somebody asked, can you do a review today? And it's actually, I was planning on that, because really today, enamines, and I'm looking in my book on enamines, and I've got one page of stuff for enamines. And you might view enamines as this big chapter, but again, my hope is that you recognize that when I show you guys that an enolate is a nucleophile, and it can react with any electrophile, right? There's a whole bunch of reactions. They're that thing, right? If you've taken Organic Chemistry 1, you should know what an electrophile is. If I tell you that this is a nucleophile, and I give you a series of electrophiles, they should not feel like new reactions. It should be the same reaction, okay? The same thing if we start talking about enols, and I tell you, right, that this is a nucleophile that's exactly analogous to the one that I've shown you here. It leads to these products with an electrophile. Right? And if there's one little thing that's different here, and you get to a molecule like this, and we'll talk a little bit more about the mechanism of this today, but this is formally the same type of oxidation state as what we see up here, right? And you can clearly see as we discussed hydrolysis of these molecules that this molecule is certainly just this here. And so again, the point of this course, right, is that when you view every reaction as its own reaction, you're going to fail, right? It's going to be the worst course of your life. But if you can make those connections and realize that every single reaction, or I would say 95 to 98% of the reactions that we've learned are really substitution, acid-base, and elimination. And so, again, everything should be viewed in that standpoint. And again, if we can sort of get through this, then it shouldn't be overly difficult. And a lot of your time should, in fact, be spent problem solving, doing challenging mechanisms, for example, really getting used to overcoming those challenges within complex mechanisms, overcoming complex challenges in synthesis problems, and really pushing yourselves to be as strong as possible, much like in the same way that a baseball player will have, 150-mile-an-hour balls thrown at them so that when they actually get to the game and they've got, the 95-mile-an-hour fastball will feel like it's slow. And so again, I'm going to push you guys, and I'm going to continue to push you guys, and you guys tend to respond when I push you, so, and respond well, okay? So, anyway, so the question becomes, we'll talk a little bit more on this in detail, but I do recognize that we're ahead and we have time, so we will review. And so what I'm going to ask is, what are the things in particular that you would like me to go over, specifically in the context of, say, for example, a problem-solving type question? That's, I think, a real good opportunity. I want to treat this to a certain extent like a recitation. Is there a specific problem you want me to discuss? Yes? So you should certainly know every reaction that you've learned to date, right? With an emphasis certainly on reactions that I will not ask a question that will say, HBr and an alkene, what's the product? I'm not going to ask that question, and I expect that you already know that. I would ask a question that would say, here's a carbonyl, but here's a ketone and methanol and an acid. What is the product? That is a reaction we've learned. So asking you specifics about a specific reaction, what reagent carries out this reaction, what is the product of this reaction? Those are questions that I could certainly ask that will just test your knowledge of a reaction. But it's really important that you understand the mechanisms. And I think that's where it can become a little bit overwhelming, right? Because you're trying to view each mechanism as its own entity, right? When in principle, especially when you start talking about reversibility, say for example, the process by which methanol condenses on a carbonyl is effectively the exact same reaction as the reverse, just with the arrows moved in the opposite direction. And so once you can start recognizing that, then the course becomes much, much, much easier. And it doesn't become, I have to memorize all these reactions, I have to memorize all these mechanisms. It becomes, even if I've never seen a mechanism before, even if I've never seen a reaction before, I can begin to understand that reaction. And once you get to that point, then the knowledge just comes, and it becomes, and it flows, and everything else. So now, previous reactions would crawl up in a synthesis problem. Now, the advantage to a synthesis problem is that there are an infinite number of ways to do a synthesis problem. I'm not going to ask you to read my mind in terms of the synthesis that I'm thinking about. And so in that extent, you've got the flexibility, right? The more reactions that you remember from Organic Chemistry 1, the easier it is going to be for you to figure out a reaction. Now, if you only know, say, 50% of the Organic Chemistry 1 reactions, it doesn't necessarily mean that you can't get a synthesis problem, right? You can get lucky, and there could just be the knowledge base that you have for those reactions lead to really clean way to make the reaction. I think at one point I remember writing a synthesis problem, and I had like 3-step synthesis in mind, and hadn't really thought of it much beyond that point. And then somebody had like a single step. I was like, yeah, you can do this in 1 step. So even in those instances, right, like sometimes the answer can just reveal itself based upon your knowledge. So it's going to be important. The more Organic Chemistry 1 material you know, the better off that you will be in a synthesis problem. But it's not like you have to know 100% of the reactions in order to do synthesis. The more you know, the better you will be, and oftentimes the practice of the synthesis problems and solving those synthesis problems can be beneficial. One of the things that and perhaps an exercise that we could do if you guys want to do today, is one that I advocate big time, right? Because you guys are always looking for more problems, right? And you're also looking for the answer keys. But the thing is that you guys, especially within the standpoint of synthesis problems, you guys can actually write your own synthesis problems for each other. And I think it's critical as students to actually work with one another. And I just saw somebody make a funny face, like, how would I do that? I'm telling you, it's very easy, right? Because what you do is you just draw a compound with some functional group, right? And I'll say, all right, here's an alkene, right? Give me a reaction that we could do on an alkene. Anything. HBr, all right, so we're going to treat it with HBr. Somebody else, I know that HBr is going to do this. Once I'm at HBr, somebody else, what can I do with that HBr? Yeah. What's that? Make it into an anion with what? Got 2 options. Well, 3 kind of. Sure, right? Yeah, all right. So, all right, Grignard. All right, magnesium. All right, somebody else. What are we going to do with that Grignard? Check ketone. All right, what ketone? Let's say formaldehyde. I guess that's an aldehyde. What's that? No, not for synthesis problem. What's that? Sure, yeah, workup, whatever. It's sort of assumed, and once you run a reaction, there's always a workup at the end. Okay, so you do this, and then you do it on your own on your paper, and then you erase all this. You give it to your friend, and you say, here, come up with a synthesis problem. Right? Yeah.
Okay, so you don't have to go for the workup, so can we go for
Yeah, absolutely.
Okay.
Yeah. So I would tell you this: if I asked a reaction question, and I said, because the workup's often assumed, but you're right. Why am I always assuming it? What if I don't work it up and I could add something else to the solution? So I would say this: there's flexibility. This is not a synthetic chemistry is not a sort of specific. There's certainly lots of gray areas in terms of what you can see. So if I have a question, I assume that there's a workup, and you show the Grignard, and you show the magnesium bromide alkoxide, I'm not going to be like, no, wrong, because you couldn't read my mind, right? I'm going to be like, oh, they just recognized that I didn't write a workup there, and that's what they wrote. So I will never penalize you for if you draw this, and you just draw the alkoxide, or if you don't show the workup. That's fine. I always assume that there's a workup at the end. If you don't want to make that assumption, and you want to make sure because I think that's, my mind is sometimes, I'm not as detail-oriented sometimes, or other people are detail-oriented. So if you're somebody that's really detail-oriented and needs to sort of draw out all those things, that's fine as well. I'm not going to penalize you for my disheveledness, right? You have I will be lenient and certainly, because you can't read my mind, so if I say, you won't be expected to, if there's no mention of a workup, unless I say no workup, before workup or something, unless I specify it, then it's fair game for you to assume either or, whichever helps you figure out the problem. So again, so does this make sense, right? And this is one of the other advantages to, I think, coming up with problems. So it's good to work with one another, because again, you need feedback in organic chemistry. I think it's very difficult to, I think, and this is one of the questions that people are having, I need to see the answers. And again, I just hopefully told you guys why I don't like giving you the answers, because there's oftentimes an interpretation issue there, and there are plenty of problems out there with answers to them. The purpose of those is to make sure that you do them in recitation or bring them to my office hours or speak to each other about, because oftentimes, more than not, you guys can find the right answer on your own, and once you're really good and capable, you get to the point where you're like, I got it. I don't even need to check the answer, I know I'm right? And that's that's the organic chemistry nirvana, if you will, right? We should all be aspiring to, all. So anyway, and the other thing about this type of approach, right, is that we all have those blocks in our memory, right, where there's this reaction and I can never, ever remember it. It's never, despite my best efforts, it's almost like you trying to remember this one reaction that you can never remember, you just can't. And it's almost like by wanting to remember this more than any other reaction, you psych yourself out or something, right? So even when you're doing these, right, you can sort of start to reinforce those reactions by being like, I'm going to draw a reaction sequence for somebody, and I'm going to sort of do something else. And so in some ways, these types of things, right, you gain in both ways, right? You sort of reinforce your knowledge of the different functional groups as you're writing the question, and then you get to practice synthesis problems in the other direction, okay? You guys want to do one of these? Yeah. So why doesn't everybody go ahead and try this? Okay, so I'm going to draw starting material, and I want each of you guys to think of now the truth of the matter is organic chemistry nirvana does not exist, but maybe within textbook and paper chemistry it does. All right, so since we're doing carbonyl chemistry, we'll start with this cyclopentanone. And the question that I have is a certain amount of steps to something. And I'm kind of curious, let's say 3 steps like you said before. You can try between 3 to 5 steps or something. If you want to sort of make it look trickier. And I'll give you guys a few minutes, and then what we can do is we can throw up some of the structures up there, and you'll see that, in fact, in the same sort of thing, we're going to have lots of different possible options, lots of different synthesis problems that we've sort of created as a class. Sort of do this. So taking some time, again, what can you do on a ketone? Well, there's lots of things that we can do on a ketone. Well, no, don't say it right now. There's lots of things that we can do on a ketone. Well, but maybe that thing that you're thinking about doing on the ketone, then it's like, I don't know what to do with this now, right? So again, there has to be this element of, there are functional groups and there are modifications that you guys have done that are what we would say sort of productive, where you've learned reactions that you can continue to do further things. But yeah, just go for it. Cyclohexanone. Cyclopentanone, excuse me, yeah, cyclopentanone. So basically start with that and just think of, what can I do on this? Anything, right? And then draw the product and the reagent. And then do another thing on whatever that is. And then continue doing that. This is how you guys can write synthesis. I mean, this is how I write synthesis problems for you guys. This isn't a lie. Right? I often try to incorporate. What? What? Let's see. See, this is great. Okay, so there's a fourth. Okay, I'll remember that one, because you just raised the point that I made earlier. You did 4 steps of something you could do in 1 step.
Oh my God, yeah.
Right,
Oh my
right?
God.
Yeah.
That's so crazy. I want to change the product.
Okay, go change your product then. But that further serves the point that sometimes even if you don't remember that reaction, right, there might be another way around it. That's why I was saying earlier, if you know every single reaction, you're in good shape. How realistic is it that you guys know every single reaction? Well, some of you will. Actually, a lot more of you than you think will know every reaction you've ever known because you guys, there's some talented cookies in this audience. Yeah. So here's one. So again, once you come up with your own problem, you can start sort of thinking about solving these synthesis problems. Yeah, it reinforces your knowledge of reactions, right? Because when you do these new reactions, right, you are then remembering the other reactions that you've had. And that's, I think, great. Got it? Oh, I got it. What's the Well, and again, there's an infinite number of compounds you can make, and then from each of these syntheses, there's also infinite number of syntheses. Well, maybe not infinite, but a lot. But you do. Oh, you did that. Yeah. Whoa. Whoa. Yes. Fine. You've got a very complex reagent here. All right, so one of your classmates got very
Fancy.
fancy. Remember, you can use any carbon-based starting material. You just have to use this. Although, if you want a really challenging question, you could start from only. Yes, that is. You can use any carbon-based starting material you want. All right. So this is the last one I'll put up here, and again, but hopefully it will make the point, right? That I think, again, the things that are the most important to me from this class primarily is that you guys become good problem solvers, right? Like, I want you guys I want to increase your work ethic. I want to make you guys problem solve. I want to make you guys cooperate. It's not a class you guys can survive on your own. I think that a common mistake that students make is that they try to tackle this course by themselves, and for these same reasons, like I said earlier, you need that feedback from someone, right? You need that. You can't just start doing stuff without feedback, and certainly the answer keys in many instances can serve as a crush, and you serve as a crush for those types of things, which is why it's important that you get the feedback, whether it's from your classmates or whether it's from myself or from your recitation instructor or from somebody that you happen to know that's good at synthetic organic chemistry or at the Learning Center, right? All right. So anyway, but here, I mean, look at this. Like, you guys could have almost just written a quiz for me right here, right? And then in each of these cases, right, there are an infinite number of different synthetic questions that we can have. So I'm not going to spend time now going through each of these syntheses, but you now have a bunch of reactions. But we can choose one and try it, but we're not going to do all 4 in class because that will take up too much time. But this is up to you guys. Do you guys want to go through one of these syntheses? Is this worthwhile for your time? Yeah? Yeah? Which one do you want to do? You want to do this one? All right, so let's do this one right here, okay? So we'll pick this one, okay, and we'll see what type of syntheses people come up with. Because if there's a lot of different options for this one, you can only imagine how many are going to be there for this one. The other type of question that I ask, I should say, when you do this, I will ask synthesis problems in multiple different forms. And some of them are geared towards doing retrosynthetic analysis. How comfortable do you guys get? Because we really haven't discussed retrosynthetic analysis too much. How comfortable did you guys get last semester with retrosynthetic analysis? Is that something you guys worked in a lot? So I'll show you another type after we go through this one. I'll show you another type of way that you can structure the questions that I think forced thinking about things from a retrosynthetic analysis standpoint. I think questions like this are often, because the way that we even came up with the questions, right, it's sort of forward thinking. But questions that I think make you, because any synthesis problem, right, it's like any problem solving, like 101, right? Like having only one method to solve something, eventually that method is probably going to fall apart, right? You often want multiple ways that you can look at the same problem, and sometimes one way will be easier than the other. That's how you get good at problem solving. And so when you write questions from a forward sense, that could be the case. All right, so I'll give you guys a few minutes on this. We've all written down these other ones. Oh, so, sorry, do you guys know, sorry, we haven't even discussed aromaticity yet. That's benzene, right? It's the same thing as, do you guys know that? All right, that was an assumption that I made. Sometimes it's drawn with a circle. I don't know if you guys have learned that yet. Now, I just realized something about this question. It actually makes it a really kind of interesting question to add dimension to it. How many steps, where did she go? Oh, she did it in 4 steps.
Yeah.
Can you?
Yes.
I don't know. Let's see it. Can you? Can you?
Well,
Can you? I'm saying, can you? Let's think about it. No, I think you're right. That was my first instinct too. You can. But then the question becomes, maybe you can, but is that the best way to do it, right? So the Wittig, what's your name again? Hava. So, Hava, do you mind coming up and showing the Wittig that you're talking about? Yeah, I mean, the question is, this is what I was thinking about initially too, but then we can think about a different level to the same question. So show the reagent that would do that in your mind.
Well, I would just, I'll cut it here, okay?
Right?
So let's do double bond instead of a positive and negative.
Yep.
pH, pH 3, carbon and carbon, and then from this carbon, which is this carbon, I would draw here.
Okay. 10-point question, I would give it a 7. Why? Well, that's a good point. No, I think this is good, but what would happen if you made that Wittig? It could react with itself, right? So there would be a major selectivity issue because you have ketone. There you go. So that's what you would do.
That's another step.
So it would be one. So I think you could do it in 2 steps, right? Because you would need to have this something else. It wouldn't want to be the ketone. And I thought the same thing you did really quickly, but then you draw it and you sort of think about it. So you and probably half the class just said the same thing.
But wait, but this is 2, okay, let's think.
Yes.
This is a phenyl group,
Yeah.
and then, right?
Yeah.
How is this going to turn around enough to hit this?
It's not.
Because, exactly, so that's the thing. This is not
But is
even going to be able to
but is it one molecule of this reacting with one molecule of this?
Okay.
Right. Yeah. So it's a solution. So you're right. If in an ideal situation, if you only had a reaction where it's one molecule, yeah. But but it's more dynamic than that, right? There's a lot more going on, so it wouldn't necessarily be, you're 100% right, that would not reach in an intramolecular fashion. And from that standpoint, right, maybe you can make the argument, this is cheap. I'll use a ton of this.
Yeah.
I'll just use a ton of this so that this never sees itself. It will only see this other one. And so you probably could do it in a single step. But it's good to think about that, right? It's, I think it's, and those are the types of tricks that a synthetic chemist could do. They could say, this takes forever for me to make. I don't want to protect it and then have to deprotect it because that's steps. This is cheap. I'll just use a whole bunch of it. So maybe I would give you more points. Maybe I'd give you the 10. But you definitely get the 10 if you said excess of this. So yeah.
But the weird thing is you're using a carbon compound. When you create the lytic, the compound needs like this reaction from that.
So and that's the point that I was bringing up earlier. I can ask a synthesis problem in different ways. And sometimes when I like to ask synthesis problems, I do it kind of the way that we drew out there. It gives you the freedom to do whatever you want, right? You can, you can draw the most complex side chain that you want within this thing because you're just saying, I'm starting from this and I want to go to this. Now, what you were bringing up is a couple other ways that we could ask these questions, right? And sometimes, if you want to sort of work on, say, for example, retrosynthetic analysis, I think retrosynthetic analysis is another type of synthesis approach, right, that can often be challenging from the standpoint of you're confusing forward with backward, and I'm so used to thinking about the forward reaction, that thinking about it in reverse can be challenging. So sometimes it's obviously, I think, inherently difficult and uncomfortable at the beginning, but that's why you have to sort of practice it, make sure that you get feedback, right? Because sometimes you could be practicing it the wrong way and just build bad habits, right? That's the other bad thing about trying to do research on your own, trying to do Freudian slip. But trying to do problems on your own. But the question that was asked is that every once in a while you will get a question like that that will say single starting material, right? So if we did the same type of question, and we said, you're only carbon-containing starting material. So this is another time that we sometimes give these problems. We can say, only carbon-containing starting material. And now we got to start to consider this, right? And so questions like that would involve this one would be like, all right, if that's your only carbon-containing starting material, and let's say, for example, I want to make this compound here. Right? And the question would be, well, how would I do that? Right? Well, sometimes in this case, you might be able to think about it in a forward sense, right? So somebody just said Grignard. Why did you say Grignard?
Because remember, you can add onto a ketone.
So what were you doing? Anybody see Barry Gordy's The Last Dragon? Old 80s movie? It's hilarious. You guys should watch it. There's a scene in it where it's like, to become the master, you must know without knowing, right? And I think you kind of might have just done retrosynthetic analysis without knowing that you did retrosynthetic analysis, right? What did you you saw this, and what made you think Grignard right away?
Because there's an OH being formed and there's a carbon-carbon bond.
So you were doing retrosynthetic analysis right there. Whether or not you knew that you were doing retrosynthetic analysis, that's what you were doing. You recognized the functional group, also maybe saw the starting material, right, and said, okay, I know that I can make a Grignard. Right? And now the synthesis problem becomes a little bit easier, right? Just that one retrosynthetic step. When you do retrosynthetic analysis, it doesn't mean that you have to do it all the way back. Sometimes it's good to practice it, because sometimes it's like, okay, now I can maybe see the answer a little bit better. Maybe. Right? How do you make Grignards? And the bromide, right? Right? And now how do we make bromides? From alcohols. How do we make alcohols? From ketones, right? Exactly. So it's this whole process where if you are able to, the advantage to being good at retrosynthetic analysis isn't to necessarily have to use retrosynthetic analysis all the way back. It's that synthesis can sometimes be like a game of chess, right? You can't think, like the human mind can only think so many steps ahead, right? So in terms of pattern recognition and so forth, you might be able to see 3 steps, you might be able to see 4 steps. There becomes a point where we reach the sort of the limits of what the human mind can see in terms of looking forward. And so thinking backwards, right, can sometimes simplify otherwise more complex problems. Now, one of the types of questions that I'll often ask that I think really force retrosynthetic analysis is when I take it to an extreme, right? If I say, I'm just making this up. I want to make this molecule here, and the only starting material that I want is methane, right? So I'm going to pick the simplest carbon-containing molecule that I can think of, and I want to build this entire molecule up from methane. And in this way, it kind of forces you. You can maybe start thinking about building this up a bit, but at an extent, sometimes it's easy to, I want to break this down, you know what I mean, and keep breaking it down, until I get to methane. But even at that point, at a certain extent, it's like, well, what am I going to do to methane? There's really only a single reaction that we know that we can do with methane. Yeah, right? So anytime you have a molecule at this point that only has carbon-hydrogen bonds on it, we haven't really learned too many ways to functionalize carbon-hydrogen bonds, and the only way, like you said, is sort of radical-mediated bromination. So I forget if it's bromine heat or bromine light, but one of these radical bromination processes, right? So again, we would make bromomethane. And from then bromomethane, we can imagine converting the bromide to an alcohol. And even within these types of questions, sometimes doing that a little bit from the retrosynthetic analysis standpoint, you can actually start to just think about that, right? You can sort of give yourself a pool of molecules that you could start to work with, right? That's another strategy in terms of synthesis. Okay, well, I have methane, like you're saying. I know that I can brominate it. Right, and then whatever heat, high heat, something like that. Okay, and then we're like, okay, well, we have the bromine. What can we do with the bromide here? We can make a Grignard, maybe, right? So we know that one possibility would be we can make a nucleophile from this. I just did something that I hate when you guys do, and I did it. That's yeah, I don't, it's like CH3Br. It's like, bromine's not bonded to the hydrogen, right? So sometimes I get lazy. But anyway, so here's the Grignard, right? And over here, right, like what else could we do? Maybe we could hydrolyze it, right? Maybe we can convert it to, what else could we turn it to? Yeah, an alcohol. How would we do that? Yeah, but how would we make it the alcohol first? What's methyl bromide? What's bromomethane? Again, this comes back to like they're not different reactions. At this point, you could probably. Can you do anything? Yeah. Well, why did you just say that? So I just heard hydroxide. What? Yeah, you got an electrophile. Make a good OH nucleophile, and that would be hydroxide. In this case, it's great, right? You don't have to worry about, say, for example, elimination, right? Because you don't have the beta protons to eliminate from. So yeah, so you can imagine CH3HO, right? And then once you're here, right, we'll say sodium hydroxide. There. This is kind of a tricky one. I always kind of feel uncomfortable. I kind of am a little bit, give you guys flexibility here, because truthfully, like, if we took this molecule and started oxidizing it, I don't actually know what would really happen, but I think based upon making analogies to what we've seen in the past, we could imagine going to formaldehyde using PCC maybe, right? But it's kind of a little weird because it's formaldehyde, and I don't really know what happened. But this is paper chemistry. It's yeah, I mean, the point is to sort of get you guys thinking about the steps and, would you be able to isolate this molecule? Like this sort of practical things. Out the window here, because it's more about being able to construct the molecules, and if you're ever actually in the lab, then you'll worry about the technical components. But again, when you start to see we're building up the components, right? We can take this Grignard, treat it with this. Now we can get two carbons together. And again, you can start to build up the molecules until you get to a point where, say, for example, then you say, okay, let me think from the retrosynthetic analysis standpoint. So yeah.
As you mentioned from the previous
Sure.
We did a Wittig.
Yeah.
And I know usually, like, when you draw a Wittig.
Aha, yeah, I know where you're going. Yeah.
Like usually you draw a single bond to the.
Oh, I didn't know where you're going. Oh, that's what you were asking. I thought you were asking about EZ selectivity.
They can do that too.
Yeah. Yeah. No, I mean, that was kind of one that's weird, right? Like, what would you guys think about this right? So I'll answer the first question and then I'll sort of answer the second question, right? The first question was, right, we can draw the Wittig in a couple different ways. We can draw it as the illid, which is probably formally more what it actually exists as, or we can draw it as the double bond, which might be more comfortable for you guys because you don't like to separate charges. This is one of these weird, we're generally used to working with that sort of second row group. We're not usually used to working with like sulfur, phosphorus, and so forth. So, it's formally more like an illid, and so this is the case. Now, the other question was, if this was going to react in a Wittig olefинation, we haven't actually discussed this one, so it's kind of nice that you asked this question. What do you guys think this would be? Why? Yeah, and the truth is I actually don't know. I could see the argument either way, right? This is sort of somewhere in between what we've seen in the past, because previously, the point that's being brought up is previously we were talking about stabilized illid versus non-stabilized illid. Primarily, we were talking about carbonyl stabilization, which will clearly stabilize that anion better than a phenyl group. But a phenyl group is clearly going to stabilize better than an alkyl group. Actually, I don't know. I'll look it up and I'll find out for you guys. But again, it's more important that you make the argument, right? If you say, it's not that, it doesn't have that carbonyl stabilization, then you would say it would go to cis. Or if you say, but it does have that, so you can make the argument either way, and I think that's fine.
It doesn't really matter with what we had before, because we had one type of.
Oh, you're right. It was symmetric. Yeah. So
It doesn't matter.
exactly. The beauty of symmetry sometimes. Okay. All right. So we've talked a bit about synthesis. Yeah. Oh, I see what you're saying. No, you're right. Well, we learned tricks. Well, but we learned. I mean, that's the thing with carboxylic acid chemistry, right? Yeah, I mean that's the beauty of a lot of this chemistry that we've been learning, right? Is that a lot of the reactions we've been learning, there's a second reaction that's simply the reverse of it. And you're 100% right. That is a complete reversible process. But water is something that we happen to have really good ways to get rid of. That's not true. What are you talking about? Dean Stark traps. You can do Dean Stark traps in dichloromethane. Yeah, you want me to tell you guys how Dean Stark trap works? Yeah. So yeah, the people, engineers are creative. Engineers are creative. I'll explain to you guys. So if you have a reaction and you're boiling, and everybody's saying, "Oh, I want to boil off the water." Yeah, but water's 100, obviously it's 100 degrees Celsius. Most solvents are much lower. So to be able to boil off selectively water, you're not going to be able to do that unless you're using like DMF or DMSO or something that's much, much higher boiling point. And even in those cases, it's probably not going to be that good because solvents will sometimes boil together, right? The two of them will together boil off. It's like when things boil, it's not necessarily one boiling over the other. Again, you guys did this experiment in first semester organic chemistry lab where you saw there was a mixture, right? And when the temperatures that were coming off were due to, say, a methanol water mixture or something like that. So what happens with the Dean Stark trap is it takes advantage of exactly what you were thinking. So on the one hand, we actually have little pellets called molecular sieves that will absorb the water. You could throw those in, and they will selectively absorb water because it's smaller than, say, for example, methanol or something else that you might have in there. But the Dean Stark trap is another option. And what it is, there's a couple different types of it. But what it takes advantage of is the fact that water is immiscible in a lot of the standard solvents that we use. Say, for example, dichloromethane, right? Dichloromethane and water will separate. Dichloromethane is more dense than water, right? And so what you'll do is you'll set up this interesting trap here, right, with a reflux condenser. Hopefully I'll draw this right. But you'll have a reflux condenser over here, so you'll boil this, and it'll be the water and the dichloromethane that will boil up, right? And then they'll condense, but they'll condense somewhere over here, right? But this is filled, right? So this will be filled to pretty much the brim, right? And you fill it beforehand. So when, say for example, the water dichloromethane, you don't want the dichloromethane to go away, right? You don't want it to all go away. You want the dichloromethane to be replenished. So what happens is this boils up, it condenses, but it doesn't condense back in here. It condenses over here. And here you have dichloromethane. The dichloromethane, oh, sorry, I'll have to show the reverse one. In this case, the way that I have it set up, it would be for something that's less dense, right? So because what you want is the water on the bottom. So in cases where the water would go to the bottom, something like ethyl acetate or diethyl ether, what would happen is the diethyl ether layer would be up here, and the water would be down here. So when it condenses down, the water goes to the bottom, the diethyl ether flows over the top, and so you don't dry out your reaction. There's also ones for dichloromethane, where now the water's on the bottom, and again, I forget exactly how it is, but it's set up a little bit differently, where it actually filters through the bottom in some way. I forget the physics, the sort of the mechanics behind it, but it sort of comes through the bottom. Yeah? No, this is Dean Stark.
Oh, that's example.
This is the Dean Stark apparatus. Yes?
So in synthesis reactor, indicate.
No, yeah, I mean, because the other thing is it's stoichiometry as well, right? You have a carboxylic acid, right? And you want to turn it into a methyl ester. How are you going to do that? Acid and OME, but what's OME? It's methanol, right? So you're going to basically use methanol as your solvent. So you're going to have a lot more methanol than you are water, right? So simply due to the Chapelier's principle, you're going to drive it. Same thing with water in the reverse, right? So reversibility is only a problem if you don't have a way to force it in one direction or the other. And so we have different ways, and water is one that we've certainly come into play a lot with, whether it's in the form of acetal formation, ketal formation, or in the case of ester formation. So, again, if you show me a carboxylic acid and you have it go into the product and you say methanol acid, fine. Yeah, you don't need to get too technical, especially in a synthesis problem. It's more important that you recognize that the reaction is there. Because in truth, when you're actually doing, the more important thing in synthesis problems, in my mind, is often not the nitty-gritty details of the individual reactions. That's more if you're interested in mechanistic studies and stuff like that. But from a synthesis standpoint, the more important thing is sort of knowing that this transformation can take place. Because I can tell you as a synthetic organic chemist, what can often happen is we never, it's rare that I'll talk to a graduate student and be like, oh, just add this, this, and this, and dump it together. Usually it's that there's a reaction that exists and you find a procedure in the literature that's close to what you want to do, and you try that. And then if that doesn't work, you'll either tweak their conditions or you'll try a different set of conditions that you can find. So it's more important to just know that reaction exists and is a real reaction, rather than knowing the details about the reagents. But you should have a sense for what those reagents are and what type of reaction it is. So reversibility I wouldn't worry too much about. All right, so we just killed 45 minutes. You guys want to move on from synthesis and do something else, or? It was a Pinnacle would have been Chem 1, right? Yeah. Okay, you guys want to do Pinnacle rearrangement? And Pinnacle is one of those cool mechanism questions, right, that involve alkyl shifts. Do you want me to just throw up a Pinnacle mechanism? Yeah, because Pinnacles, I think within the sort of classes of different, within the sort of groups of different complexities of reactions, right? Sometimes I think the mechanisms that can oftentimes be the most complicated are ones where you actually see carbon rearrangements, and certainly Pinnacle rearrangements are ones that do that, right? Because you get this 1-2 migration. So just as a reminder to everybody, because it sounds like I hear people trying to remember what Pinnacle rearrangement is. The Pinnacle rearrangement is formally a process, and we'll actually see a similar version of this once we start talking about nitrogen-containing molecules, that is at least mechanistically similar to this. But really what a Pinnacle rearrangement is, at its heart, again, it's thinking about things not really being the same. Are you guys... Well, I'm going to try to put this into perspective in terms of what you guys know, right? It's oftentimes, you shouldn't view a reaction as its own entity, right? But something that you guys have learned, right, who knows what hyperconjugation is? Show of hands. All right. So hyperconjugation, right? It's always going to build off of something, right? So we know hyperconjugation exists, right? And that's one of the whole reasons why when you have a whole bunch of the reason why more substitution, right, leads to better stabilization is that you surround the molecule, right, with these carbon-hydrogen bonds, and these two electrons can sort of help donate into that pi cloud and stabilize it, right? Right? What happens, so let's now move to the next step. What happens when hyperconjugation goes a little too far? What's that? It's going to yank that entire bond over. Yeah, right? This is a 1,2 alkyl shift, or 1,2 hydride shift, as I kind of have outlined here. So the same sort of idea of hyperconjugation, those electrons being pulled towards that pi system, right? This same phenomena, right, you can sort of think of within the context of 1,2 hydride, 1,2 alkyl shifts, right? You have that carbocation over there, it's stabilized. Well, oops, I got a little too, yeah. So anyways, so whether it's a 1,2 hydride, whether it's a 1,2 alkyl shift, you guys, this is one of the things that you know. So again, just to sort of complete that thought, right, what's happening is, formally you have now, again, it's primary carbocations as I've drawn, but that's just the general idea, right? You're pulling the two electrons away from an entire bond, and again, you can sort of think about it in the same way as you think about hyperconjugation. All right, so let's think about a pinnacle rearrangement. And this is formally what a pinnacle rearrangement is. It's just a really good alkyl shift. So the process is you generate carbocation, and you're set up in a system that's actually really well stabilized to do a 1,2 alkyl shift. Now let's discuss why that's the case, right? If we propanate this molecule, which you can all do, you can all do this, hopefully, right? Again, because we're going to generate that carbocation. The next step, right, is simply water leaving. Perhaps we can set up a Dean Stark if we want to. And then, right, we're set in a situation where now we've got that carbocation, right? Drawn in the same way we have over here. And you've got groups that can migrate. And when we think about what those groups are that can migrate, one of the things that really makes pinnacle rearrangement take place really well is you start to realize that up here I have this primary carbocation, right? Here, what happens when I do that shift? Absolutely. Say it again. Yep. One more time. Resonance. Right? So we have a carbocation that is even better than, say, for example, the tertiary carbocation that we had over here, again, because we have that resonance. And again, then that resonance form is simply a resonance form, we deprotonate, and then we get to the product of the pinnacle. So again, pinnacle is just a really nice way to, and it's just a really well-stabilized 1,2 alkyl shift. Again, because of what? Resonance, yeah. So anyway, so this is the pinnacle rearrangement. What can become difficult about pinnacle rearrangements is that to provide a really good avenue for me to ask really challenging questions that involve alkyl migrations. And sometimes that can really come down to just being really comfortable at drawing molecules. And this is why I often stress to many of you guys that come up to my office and you start drawing stuff on the board and it looks like chicken scratch. And I say, organic chemistry is as much an art course, right, as it is in many ways a synthesis course. If you're drawing the molecules and they are awful looking, then sometimes you can even screw yourself up, right? Because you have a bond that's shorter than the other, and then you redraw it and you forget that that bond's there. So it's really important that you draw these well, and it's good that you get in the habit of drawing. So anyway, so from the standpoint of a complex alkyl shift type mechanism, you can do mechanism problems, right? Again, it's going to be formally the same kind of idea, but sometimes when we involve things like rings, we begin to have some issues, simply because we've added a level of complexity to the actual drawing, right? Which I think can sometimes make this challenging. And again, if I told you to predict what this product would be through a pinnacle rearrangement, there might be multiple possible answers that I would all feel as reasonable. Yes?
That's for the oxidation mechanism. Yeah, right. Yeah. So isn't like the oxygen from the way
So the question was asked about inductive withdrawing versus electron donating, and it's a fair question. But resonance is just awesome. So yeah, no. If things can achieve that resonance stabilization, and we'll see this a little bit in aromatic chemistry, because there are instances specifically in aromatic chemistry where we'll still see this type of donation, specifically of halogens through aromatic systems. Because you think about fluorine, and you're like, well, fluorine wouldn't do the same thing. Oxygen happens to just be a little bit better of a donor. It's not necessarily as electron withdrawing, and so there is that component, but the resonance stabilization really trumps it a lot. Okay, so here, right, we can imagine a lot of different mechanisms that you might be able to draw, a lot of different products. And let's start with that question. Let's start with that. That might be a little bit more challenging. There's a couple different products that I can imagine drawing here. There's actually two. Well, I want people to try to draw this. What? You were saying some IUPAC that I would probably have to see. Yes, yeah. But yeah, so you take this and you treat this with acid, and we want to do a pinnacle rearrangement. And really what we have here is we can protonate this one and have a carbocation here, or we can protonate this one and have a carbocation there. Each of those are going to lead to different products, and for the sake of argument, I would never expect you, and I personally wouldn't be able to perhaps predict which way it would go without thinking perhaps a little bit more of the overall energetics of the system, which might require more research into this. But again, there's two possible products. One of them should be fairly easy, right? If we protonate this one here, and we lose water, right? That one should be fairly easy. Right? Because now we have that carbocation, and it should kind of be fairly easy to see that, okay, I'm just going to get the 1,2 alkyl shift. I'll just push that resonance arrow down there, and then again, and then we'll deprotonate it. So we'll get to here, then we'll deprotonate it, and we'll get to the ketone there, right? So that I think is the easier one of the two. What I'm going to ask you guys to do is try to draw the other one. And some of you might be able to do this really easy. It'll be like, it's no problem. You might be an art major. But for some of others of you, I think perhaps it can be a little bit challenging just because, when you want to maybe count the carbons, again, take care to make sure that you've obeyed, conservation of mass. But again, the one that I'm talking about is right, what I'm talking about is from that carbocation, right? In this case, if we do that migration, what are we doing? Yeah, we're doing it, well, not a ring opening, it's a ring expansion. Right? So we're going from a 5-membered ring, and we're kicking it out one, right? So this carbon, right, or sorry, I should say this carbon is going from outside the ring to inside of the ring, and we're not moving any others around per se, so really what we're just going to is from a 5-membered to a 6-membered ring. So in many ways, this might be an easier one to see, but I would say that sometimes it's even still worth it to just count, right? And you can sort of number your atoms, right? And so the OH would be at 1, right? And so we see that it's going to be a 6-membered ring. Right? And then at 1, right? And again, you see what's the bond that we're making, right? It's between 5 and 6. Right? So we basically, the bond on 1 that we had previously is no longer there, right? So that's going to take up a positive charge. We've made a bond between 5 and 6, so you go back over and you double check your answers. Now you got the bond between 5 and 6, right? And then obviously this is going to resonate down, deprotonate. Okay. So, yeah, so I think there's more challenging questions that are of the same type of area, which may be kind of what you were asking about. What I would say for those types of cases is try it again and just take, those are hard, those are really hard questions. I don't know that I want to spend time up here doing one of those, but again, what you want to do in those questions is take the time, perhaps number the different carbons, and think like I just did there, right? Obviously this is perhaps a simpler looking one, but just sort of think about that. Where is the bond forming, where is it breaking? If you have to map your atoms, right, and then map them into the product. Sometimes what some people like to do, sometimes, here's another hint, or not hint, here's another tip that sometimes I'll even do, especially with the more complex compounds, is instead of saying, oh, it's a six-member ring, I'm going to go ahead and I'm going to draw a nice looking six-member ring with all the good angles and everything else like that. You just draw it really cruddy looking, like this, right? And sometimes what I'll even do is I'll just redraw the molecule. Right, I'll just redraw the molecule over here, right? Because sometimes you guys will do it on top of the problem. That's not going to work, obviously, on an exam or a quiz. I allow pencils on exams and quizzes, so you can certainly do this. You just redraw the molecule over here. And you say, well, what am I doing? Well, I'm breaking this bond, right? And I'm making this bond, and I'm moving that carbocation over here. And again, it looks really crappy, right? Like it doesn't look good, but at least all your bonds are in the right places. Then you can redraw it and make it look better subsequently. So that would be another tip that you could have specifically, and this actually works out really well with perhaps some of the more complex looking targets, because that's a lot of mechanism problem solving as well, is just seeing it in the right way, being able to look at it. Sometimes you're looking at it one way and it's just, you can't see it that way, and so you just have to redraw it in a different way. So a couple options here would be like, oh, six-member ring, let me just go ahead and draw it as a better six-member ring and fill in the dots later on. But here's another option, is you just redraw the molecule over here. I wouldn't do it on top of the molecule, right? Especially if you're practicing at home, I would still take the time to go ahead and redraw it, even though if you feel like I don't have enough time to do all this. Just spend the time. Redraw it out, because what can happen is if you start erasing things, you'll forget what was over there. So you want that reference point to go back to, and certainly, obviously, on an exam or a quiz, you're not going to get credit if you start doing things like that. Yeah?
Should we review one nitro and one alcohol?
Sure. Okay, so I think this goes back to perhaps the question that we asked earlier, right? And that's that all of the chemistry, or a very large percentage of the chemistry that we have, even if it's talking about intermediates, right, is really just nucleophile, electrophile. Again, I'll just draw this as positive and negative just to make it work well. Right? And we're basically forming this bond. And so a lot of sort of being able to associate these reactions with one another simply comes down to identifying and asking the question, is this molecule nucleophile? Or then what's the electrophile? Or if I've got a good electrophile, what could be the nucleophile? And back and forth. And we've seen a lot of different things. In essence, anything that has lone pairs can serve as a nucleophile, right? Anything that could perhaps be resonated, for example, or have a bond break where it can have a positive charge on the flip side, could be an electrophile. So when we start thinking about, say, for example, Michael products, or when we start thinking about aldol products, really what this comes down to is in all cases, it's the same nucleophile, right? It's a nucleophile that we spent an entire day or last class on, right? And what we're referring to, right, is molecules of some type like this, right? Which in principle, from a reactivity standpoint, as we learned, don't worry about the O alkylation. Obviously, you probably all recognize that oxygen couldn't cap, but we're not going to worry about that. We're going to worry primarily about C alkylation to simplify matters for you guys, and so this is perhaps how you might like to draw it. Or if you want to draw it as the other resonance form, again, you're never going to be penalized for drawing one resonance form over the other, unless I ask a question specifically referring to resonance forms as an important component of the question. Let's say, for example, on a mechanism question, you can draw both, you can draw either or, but it's really this one that perhaps is the one that reflects how it behaves as a nucleophile. Analogous to any other nucleophile we've seen, right? Analogous to alpha-lithium, analogous to alpha-grignard, analogous to anything else. It's just that there's this other group over there, carbonyl plank. So that's the nucleophile, and they both have the same one. So, and with the electrophiles, again, it's simply a matter of the two different types of systems. I mean, we're talking about carbonyl-based electrophiles, right? And anytime that we have a carbonyl-based electrophile, right, we draw it in the same way as we talk about the same way as we talk about this is how we'll often draw it, this is the way that it will react. In the case of a carbonyl, right, this is oftentimes the way we draw it, but really this is the way that we think about it reacting. Right? And so from an aldol standpoint, right, I think perhaps what can be complicated, if I gave you this, and I gave you this, and I said, what do they make? You guys could have probably all told me that, in your sleep, right? The challenge becomes when I show you this, and I show you this. And so in many ways, the first thing about any of this sort of aldol-like chemistry is recognizing resonance forms that might illustrate the reactivity of them and how they behave, right? And so I think that's one of the things that makes enolate type chemistry challenging. This is often how we draw it, this is how it reacts. Carbonyls, this is how we draw it, but this illustrates how it reacts. Take to the next level, right, with alpha-beta unsaturated, right? Or I could just draw on top of this. We just have an additional resonance form. Right? And that resonance form is the one here. Right? And again, both of these, as we said a few classes ago, both of these are resonance forms that can, in fact, illustrate the reactivity of these species. In some conditions, we see it react in this way. We said Grignards, alkylithiums, right, react in this way. Cuprates will actually react down here. In the case of an enolate reaction, it will always react down here. And again, this is where we don't want to get into too much physical organic chemistry per se, but it's the sort of idea of, again, you have to sort of get into homo-lumo sort of energetics of it. And again, this goes much, much deeper, but the general idea here is that this is where the lowest LUMO is on this conjugated system is here. So in general, a nucleophile is going to want to react here. Only in cases where you have highly charged, highly dense, what we call hard species, does it react in a way that reflects where the more electrostatic interactions take place. And that's, again, just because this carbon is closer to the oxygen. This is the more electronically poor carbon, and this is why things like alkylithium and alkyl-Grignard, which are more densely charged, would react here. And enolate, we can think of is that charge being spread out a little bit. So it's not as densely packed with that charge, and so it's not as likely going to react here. Instead, it's going to react where the LUMO is, in the same way that a cuprate would. And so again, if I gave you this, and I gave you this, you're golden. And so that's what you need to do to sort of understand these reactions a little bit more, to draw them into the resonance form, draw them into the reactive forms. It's perfectly fine. Again, the resonance form is the same thing. You're never going to get penalized for drawing a resonance form of the molecule. And so, once you get more sophisticated, like once you're a PhD student or something, when you go to get your PhD in organic chemistry, as I know you're going to do, right? People start to then get a little bit more picky about how they draw them, right? Like, let's draw them in the one that's more stable. But at this stage, I want you guys to recognize how the bonds form, and if you draw them, however resonance form, whichever one helps you, is going to be better. So does that make your life a lot easier?
One thing, the stronger the nucleophile,
The more charged, the more densely charged, I guess you would say. Yeah, it's this sort of this hard, soft. So what they're kind of referring to is, so you understand that the in general nucleophile will want to react where the LUMO is the lowest, right? And so that's the sort of general thing, any nucleophile. But there are instances where electrostatic interactions, so negative, positive charge, that's what I mean when I'm saying electrostatic interactions, where those will actually then influence the relative regioselectivity. In a case like alkylithium, where you've got that dense negative charge, that dissociative negative charge there, that will then be induced to go where this molecule has the best delta positive, which is the one that's closer to the carbonyl, because the carbonyl is so good electron withdrawing. Does that make sense? It's a little bit advanced, but if you understand it, I think it's not too hard to understand.
In some cases, you'd rather attack the LUMO.
In all cases, it's how do I say this? The nucleophiles will always want to attack the one that's the better LUMO. The
Negative charge.
no oh my God, I got like 3 hours of sleep last night. Oh my God, the whatever to the rule, oh my God. I'm gonna need a coffee. Whoever's coming to office hours, I need to get a coffee before I go to office hours. The few times when it's different have to do with electrostatic. There's a common saying. I'm just losing it right now. All right, we have time for maybe one more question. But but only in cases where electrostatic interactions can overcome that. That's when you can see it. So it's
They're almost always Lumon.
it's generally the 1-4. All right, last question. Bye, guys.
You said why Gilman's react differently with letting Grignard carbon derivative, why like Grignard has 2 on.
So we'll have time for another question because this one will be very quick. We'll discuss that, and I'll give you a great explanation when we get to cross-coupling chemistry because it's actually an entirely different kind of mechanism. Okay, we have time for one more question. So we'll come back. Ask me that in about a month and a half. All right. One more question. Yeah. In this one here, that's what I'm saying. It's the one closest to the carbonyl, right? So that's why, since that one has, and that's why the electrostatic interaction. All right. If you come up to my office hours, I just have to make myself a quick coffee, obviously, because I'm a little out of it today. So.